It is time for part 2 of 5.8 here. We're going to be dealing with the logistic model. All right, so with exponential growth, with our exponential growth model, assumes uninhibited growth, meaning it just grows without bound, right? It just keeps going. But we know that it's not like a population of, say, deer or rabbits or whatever are just going to keep going to infinity. Something is limiting it, right? It has what we like to call a carrying capacity, okay? So if we look at our logistic model here, P of t is equal to C over 1 plus A times E raised to the negative, or the opposite of B times T. So we still have some parts that E to a power with our time there. So some similarities in the formula, but we have A, B, and C are all constants. They're all numbers, okay? A is greater than 0 and C is greater than 0. And then if it's growth, B is greater than 0, and if it's decay, then B is less than 0. And that makes sense, right? We've dealt with that before. However, be careful. There is that opposite of B up in our exponent. So if that number is negative multiplied by time, it is actually growth because the B value would be positive. So be very, very careful with that. You can almost think about it how it's in the denominator, right? So the exponent, if it were brought to the numerator, not that you can because of the addition, but if it were, it'd become positive. That's the one way that I remember it, okay? So let's look at these properties of our wonderful logistic model. The domain is the set of all real numbers, and the range is the interval from 0 to C, where C is our carrying capacity, right? That's like our upper limit in this case. So there are no x-intercepts. The y-intercept is P of 0. That's pretty standard across the board, right? If I plug in 0 for my x values, that's my y-intercept. Cool. 2 horizontal asymptotes, one at 0, one at C. We have increasing if B is greater than 0, but remember that would look negative in the exponent because of that opposite of B in my formula there. And then we have decreasing if it's B is less than 0. We've got an inflection point where it starts like increasing less. Okay, that's what we call an inflection point. You'll deal with that a little bit more in calculus, but it's where we're going up and then it changes. So it's at its steepest point right here. That would be our inflection point. Okay. And that's when it's half of the carrying capacity. And then describes that a little further of what I was just saying. And then we have, it's smooth, continuous, no corners, no gaps, nothing like that. Okay. So wonderful properties of our logistic model. Either take a screenshot, write it all down, pause the video if you need to, because we are moving on to an example. Alrighty. So we have, a population of an endangered species. Now, bald eagles, if you did not know, endangered at one point. I think they're on just they're just protected now, but for a while they were endangered. I could be wrong about that. Voice crack, I'm leaving it. So environmentalists often capture an endangered species and then transport that species to a controlled environment where it can produce offspring and then regenerate its population. Now, we're going to say, suppose that 6 American bald eagles are captured, transported to Montana, and set free. And based on experience with this, they have a population model here, a logistic model, to estimate what that population might be as time goes on. Right? It's not like it's exact; it's an estimation. Okay. So it says determine the carrying capacity of the environment. Well, we know that value C up in the numerator, 500, would be the carrying capacity. That's what they're saying is big of the population we're going to get of those bald eagles. It's not going to go above that. Okay. So 500. American bald eagles. Cool. What is the growth rate of the bald eagle population? Well, my growth rate, notice how it's negative 0.162. Remember, it was opposite of B, so it's 0.162, or we're going to have, move the decimal twice, so 16.2%. All right. Growth. Lovely. It says use a graph to graph P of T and sketch the graph noting any important features. All right, so I've got it plugged into my my TI-84 here, plus Silver Edition emulator, and I'm going to need to adjust the window. Now we could do zoom fit, but I'm thinking I got a decent idea as to what I want to do here. So let's think here. We've got 500 is our carrying capacity. So for my Y max, I'm going to go above that. I'm going to pick 600 so I can see it start to flatten out. For my X min, that's my time. I could leave it as -2. I can make it 0. I'll go with 0, I guess. Okay, because I don't really care what happens before time. It's just when it starts. And then my X max, let's go for like 100 years. Let's see what happens over 100 years. And let's graph it. That's a pretty cool looking graph right there. All right. So note any important features. Well, I'm going to go ahead and screenshot this and pop it into the presentation thingy. All right, so I've got my screenshot there so I can write on it. What are some important features here? Well, we can see we have the carrying capacity, and I'll actually bust out a ruler real quick, keep it nice and straight. I know I'm going to have that asymptote of y equals, should go with red here, y equals 500, okay? And I've got one at 0 as well. Y equals 0, that is. So this is y equals 500. That is my carrying capacity, right? I feel like I should have done that as a dashed line. I'm going to do that. I'm going to do a dashed line. I apologize for that. I apologize. Let's pop that ruler back out. And then I forget that I can do a dashed line pretty easily. There we go. Then I've got my inflection point right here, right? So that's where my half of my carrying capacity occurs. Point of inflection. Let's see here. Anything else we want to do? We can label our axes. We got our time. Should be our T. And then we have our population. Of eagles. Cool. I think that's overall pretty good. Wonderful. Let's keep going. It says, what is the population after 3 years? Well, once again, I can actually use my graphing calculator to do this, which is pretty nice. I can just hit second calc, and after 3 years, I can just put in 3 for X, which is my T, and hit enter, and I'm going to get 9.682, so roughly 10 eagles, right? So I did P of 3, 9.682, or roughly 10 eagles after 3 years. So we've already seen the population grow a bit. That's awesome. Then it says, when will the population be 300 eagles? Well, what can I do to figure out when it's going to be 300 eagles? Well, why don't I take out, once again, my graphing calculator, since I already have it in there. And I can't plug in a value, but I could put in another equation here and say 300. We've done this before. Graph. And I'm going to find out where that intersection is. So second calc. 5 is my intersect. And I'm going to hit enter. Enter, and there's only one intersection here, so if I just hit enter a third time, it's going to bring me right over to it. 29.7296. So we're talking about 30 years almost. So I'll put it. I'll put the decimal in there. 29.729. So, and that rounds up 27.73 years. Lovely. So. And I'll throw a 0 there, showing that we rounded it to 3 decimal places. 27 3/4 years almost. Now here it says, how long does it take for the population to reach 1/2 the carrying capacity? Well, what was our carrying capacity? Carrying capacity was 500, so half that is 250. So we're going to do basically the same thing that we just did, but now I'm going to throw in 250 for my second equation. Not too bad. Graph it again. Graph it again. I do love watching that thing graph. It's an exciting thing to watch. All right. So intersect, which is 5. Hit enter 3 times. Again, there's only one intersection, so it's going to go right to that. It's when you have multiple intersections that you really need to make sure that you guess accurately so your calculator gives you the right one. So it says 27.2267, so 27.227. 27.227 years. Lovely. Whew. That was some good stuff right there. I like it. Very nice. Very nice. Again, you could have done part D here with substitution directly into the equation, but I already had it typed in, so why not use my calculator, right? And then a couple wonderful little intersections there with our TI-84 Plus Silver Edition emulator. Excellent. Let's do one more example. You know, before we move on here, I want to show you guys something cool. Last summer, we were up north at our cabin, Northwoods, Wisconsin, near Minocqua, Wisconsin, if any of you have been there. And we have a couple bald eagles that live on our lake. I think generally speaking, one pair of bald eagles has their own like body of water. You don't usually have 2 families of bald eagles living on the same lake, is what I've heard. Maybe that's just urban legend. But anyways, this year, or that year, last summer, we had the craziest amount of bald eagle activity that we've ever had. It was so cool. And my brother-in-law is into photography, and he picked up a couple eagles right here and here. There were so many pictures. They got so close. One took off and flew right over their kayaks. And then even got one of I believe it was an eaglet, a baby eagle, I believe, eating a fish. Okay. Now, if you're not one to want to see nature in action, then look away for 2 seconds. But I mean, that is pretty cool right there, right? No guts or anything, but that is a cool picture. I mean, how often do you get to see that? All right, it's gone. So pretty awesome, don't you think? Indeed. Bald eagles are awesome. That's why we're saving them, and increasing those populations using a logistics model to estimate what their population might be in the future. Okay, let's keep moving. Fruit flies could happen to anybody. All right. Fruit flies are they increase like so fast. So population of fruit flies can be modeled by that function. Now, like you'll see like, oh, I got one fruit fly. And then all of a sudden, like a day later, it's like, why are there so many fruit flies? Here's why. Okay. So we got this function here where P of T represents the population of fruit flies after T days. What is the carrying capacity? Again, these are problems that we might ask just on the SAT. No math really involved. It's just asking if you understand what's going on with this particular function. Well, for our carrying capacity of this one, it is 230 fruit flies. Okay, that is our C value up in the numerator. Determine the initial number of fruit flies and the growth rate. So for the initial number of fruit flies, we actually don't get to just like see it in there, kind of like the APERT, or the, any of those exponential growth formulas. It's not actually shown in here. But if I plug in 0 for T, when time starts, that's the initial number of fruit flies, right? So let's do that. Let's do P of 0 is equal to 230 divided by 1 plus 56.2 e to the negative 0.37 times 0, because I'm substituting in 0 for T. So anything to the 0 power, because this is going to be 0 up in the exponent here, anything to the 0 power is 1. So I have 1 plus 56.2, so 57.2 would be in my denominator. If you want to make it a little easier to plug into your calculator, it's nice to do some of these more simple things outside of the calculator so you don't mess up with parentheses and things. So I did already calculate it. It is 4.021 fruit flies. All right, and our growth rate here, is that negative the 0.37, so a 37% growth rate. Cool. Remember, it's the opposite of B up there. That's a crazy big growth rate, which is why they all of a sudden you're like, there's so many. It wasn't even that long. What is the population after 5 days? And maybe we look and see. Looks like we're going to have to plug this into our calculator here by part D. So I'm just going to plug it in right now, and we'll use that. Alrighty, so I have it in my TI-84 Plus Silver Edition emulator, and I've adjusted my window accordingly. I went for 50 days. That seems pretty decent. And I changed my WiMAX to 300 since my carrying capacity is 230. I wanted to see a little bit above it. Everything else stayed the same, so let's go ahead and graph it. And remember, we're going to be able to know what the population is after 5 days by just plugging in 5 for X, which is my T value. So if I plug 5 in, or you could substitute it directly in for T, but I find this to be a little bit easier because if I'm going to use my calculator later, why not use it to do the substitution for me? So 23.382 when rounded, 23.382 fruit flies after 5 days. So roughly what, 23 fruit flies. You're not going to have a partial fruit fly. And then we have, how long will it take for the population to reach 180 fruit flies? Well, we can use our graphing calculator, but I'm going to have to add in another equation here, and we're going to throw in 180. And we'll find ourselves an intersection. Okay, so how long until 180 fruit flies? Let's find that intersect, which is option 5. Enter 3 times. We only have one intersection, so I don't have to worry about the calculator picking something else. And it's going to be 180 fruit flies after 14.3509, so 14.351 days. Nice. Alrighty. Part E here, and then we're done. How long does it take for the population to reach 1/2 the carrying capacity? Well, if we remember, our carrying capacity is 230, so half the carrying capacity would be 115. So let's head back to our TI-84, throw in that 115 for my Y equals, and find that intersection. Man, we're going to get good at this. We're going to get real good. And then you'll be like, hey guys, don't leave that rotting banana out. You know, we're going to get fruit flies. And I'll tell you what, I can tell you how many fruit flies we're going to have after a couple days based on the initial amount of fruit flies I found and then how many later on. And you're going to be like throwing out logistics models all over the place. And you'd be like, you know, half the carrying capacity is 115 fruit flies, stuff like that. You know, it's going to be awesome. Alrighty. So let's find that intersection. That was good. We killed some time while the thing graphed. Alrighty. First curve, second curve. And when they say first curve, second curve, they just mean like the line, the equation that you're selecting. And guess, and I've got 10.8889. So 10.889, 10.889 days. Woo! That's what it's going to be for it to reach half the carrying capacity. Remember, it's going up like this, right? Concave, upward, and then whoop, changes. That's right where it changes at that point of inflection. It's getting steeper, 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 and then less steep, less steep, less steep. Cool. That's pretty exciting stuff, isn't it? I would say so. Hope you guys enjoyed it. I know I certainly enjoyed it. Hope you enjoyed the eagle pictures. Those are pretty awesome. And what would a video be without the one and only River Dog Jenny on the gram here? Hope you guys had a nice day. Hello, Jenny. You ready to do some math? We're going to do some more math together, but that's it for this one for us, right, Jenny? That's right. All right. America, freedom, rock and roll, Costco, River Dog Jenny on the gram. Have a great day, guys. See ya.